In 1973, as oil prices quadrupled overnight, France faced an impossible bet. It had to choose whether to gamble on Jean Bertin's futuristic hover train, which had just shattered records at 430.4 kilometers per hour, or to commit to reshaping steel rails forever. How did a nation on the economic edge engineer the world's fastest trains, and at what cost to its dreams? The answer begins with a crisis that changed everything. Oil soared from $3 to $12 per barrel in a matter of weeks. For French planners, the numbers were not abstract. They were a blunt force, slamming into every calculation of national survival. Imports drained the treasury, and the price of keeping trains, factories, and cities running climbed each day. In Paris, government offices filled with the low hum of urgency. Reports stacked on ministers' desks warned that France's dependence on imported energy threatened not just comfort, but sovereignty itself. Transport, long overlooked, became a battlefield for economic security. The state set new targets. Rail would need to capture at least 1/4 of intercity travel, up from barely 10%. The ambition was not simply to move people faster, but to insulate the country from future shocks. Every mode was scrutinized. Aviation, once the darling of progress, now looked wasteful. Motorways, symbols of modernity, seemed vulnerable. Only the railways, if they could be transformed, offered a path to resilience. Yet transformation demanded choices. The budget, already strained, could not support every vision. Gas turbines, once promising for their power, now looked like liabilities in a world of volatile fuel prices. Electric propulsion, tied to France's growing nuclear grid, promised steady costs and energy independence. Behind the closed doors of ministries and planning committees, the debate sharpened. Would France gamble on radical new technologies or reinforce what it already knew? The answer would shape not just the trains, but the future the country dared to imagine. What does it mean to build a future that never arrives? On the outskirts of Orléans, a ribbon of concrete still cuts through the fields, a monument to a vanished dream. In 1974, the aerotrain hovered above this track, propelled by turbines and by the promise of frictionless speed. Jean Bertin's team coaxed their air-cushioned prototype to 430.4 kilometers per hour, a number that outpaced every steel wheel on Earth. The I-80 HV glided at a whisper, skimming 5 millimeters above the guideway, its turbines roaring against the wind. For a brief moment, France seemed poised to leap beyond rails entirely, but the future can turn on a single meeting. In Paris, cabinet ministers gathered behind closed doors. The oil crisis had redrawn every budget. Gas turbines, once symbols of progress, now looked like liabilities. The aerotrain's guideway demanded new land, new concrete, new money. Electric trains, by contrast, could run on the growing nuclear grid using tracks France already owned. The vote was swift. Funding for the aerotrain ended. Contracts were canceled, and Bertin's letters, full of calculations and hope, were left unanswered. By the end of that year, the Orléans test track fell silent. The concrete guideway stood unfinished, its surface gathering dust. Bertin, denied the chance to prove his vision at scale, would not live to see another prototype. The world's fastest hover train became a relic, its record unchallenged, its promise abandoned. In that silence, the path closed, not with a crash, but with a signature. The engineers who had watched the hover train fly now turned back to steel and wire, carrying the weight of what might have been. Steel and electricity became the raw material of a new vision. The TGV form was dictated by engineers determined to extract stability from speed. At nearly 200 meters in length and weighing close to 400 tons, the SNCF was no fragile experiment. Its mass was distributed across 8 articulated cars, each joined by shared Jacobs bogies, an innovation that did more than save weight. By connecting cars in this way, the train resisted the lateral forces that threatened to tip or derail at high velocity. The bogies themselves, compact and precisely engineered, cut unsprung mass by over 3 metric tons compared to conventional designs. Less unsprung weight meant less vibration, less wear, and more control, as the train swept through long curves at 300 kilometers per hour. Power was concentrated but not overwhelming. 8 asynchronous motors, each rated at 1,100 kilowatts, delivered a combined 8,800 kilowatts to the rails. These motors were not simply bolted to the axles. Engineers mounted them to the car bodies, further reducing unsprung load. The effect was subtle but profound. Smoother running, higher reliability, and a train set that could endure the relentless demands of daily, high-speed service. Every dimension, every connection, was a negotiation between ambition and reality. The TGV structure was built to scale, able to absorb the stress of record attempts, yet refined enough for routine journeys. It was a blueprint of power, not just in numbers, but in the quiet confidence of a design that could be trusted at the edge of possibility. On the morning of April 3, 2007, the eastern plains of France became a proving ground for the limits of steel and wire. Engineers gathered along a freshly prepared stretch of the LGV Est, watching as a train set unlike any before rolled out of the sidings. This was the V150, a TGV POS rebuilt for a single purpose: to chase a number no other wheel on rail train had reached. The train itself had been pared down to its essentials with 2 power cars and 3 passenger cars, a total length just long enough for stability, but short enough to shed every surplus kilogram. The wheels, normally 920 millimeters in diameter, had been replaced with giants measuring 1,092 millimeters in diameter, each turn eating more distance, each revolution tuned for speed. Above, the catenary wires thrummed with energy. For the record attempt, the overhead voltage was raised to nearly 32,000 volts, well above the standard 25 kilovolts. Substations along the line were recalibrated, feeding the train with current as it accelerated. Track workers had tamped every sleeper, aligned every rail, and added ballast to absorb the shock of unprecedented speeds. Over 3,000 kilometers of test runs had exposed every weakness, every whisper of instability, and each one had been addressed in turn. At 1:13 p.m., the V150 reached 574.8 kilometers per hour. The telemetry captured a fleeting equilibrium, wheels spinning faster than any before, pantographs holding steady contact with the wire, engineers in the cab silent but for the hum of transformed power. For a few seconds, the train ran ahead of its own shadow, a living answer to decades of calculation and hope. Then, as the brakes engaged and the world slowed again, the record stood, unmatched and, perhaps, unrepeatable. Speed is not simply a matter of power. Every additional kilometer per hour demands exponentially more energy. At 300 kilometers per hour, aerodynamic drag already consumes the majority of a train's power. Force rises with the square of velocity. But the power required climbs with the cube. Push past 350 and the numbers become unforgiving. The V150's world record run needed over 19,000 kilowatts, 3 times the power of a normal TGV train, just to overcome air resistance. Yet even this achievement existed in a carefully engineered vacuum. Reinforced catenary wires, raised to nearly 40,000 newtons of tension, allowed the pantograph to maintain contact at speeds approaching the transverse wave speed of the wire, about 200 meters per second. Beyond this, the system itself begins to fail. Waves ripple ahead of the train, the pantograph lifts, and energy arcs in blue flashes. On ordinary lines, the cost of building catenary and track robust enough for such speeds rises to 35 million francs per kilometer, a figure that dwarfs any practical return. And when safety falters, the consequences are immediate. In November 2015, a TGV test train derailed at Eckersheim while running at 352 kilometers per hour. 11 lives were lost, in a moment that underscored the difference between what is possible and what can be sustained. For engineers, the lesson is sobering. The physical world draws its own limits, indifferent to ambition or pride. The Orleans Guideway endures, a concrete spine stretching across the landscape. Its surface cracked and overgrown, but unmistakable, a silent artifact of the Aerotrain's vanished promise. Nearby, the I-80 HV prototype sits in quiet retirement, its brushed aluminum skin dulled by time, preserved not as a machine of the future, but as a relic in a museum. These remains are more than curiosities. They are the physical memory of a country that once believed speed could be reimagined from the ground up. Yet the vision did not die within France's borders. The technical lessons of the TG5, articulated cars, high-voltage electrification, the discipline of routine high-speed service spread outward. Contracts carried French expertise to South Korea's KTX and Spain's AVE, where trains built on these principles now cross continents. In export, the TGV became a blueprint, its DNA scattered across networks far from its birthplace. Back home, the operational ceiling remains fixed at 320 kilometers per hour, a limit both respected and enforced. The prototypes that once chased records now rest behind glass or gather dust in depots, their shapes familiar only to those who remember the first days of ambition. Along the Orleans track, wild grass grows between the pylons, and the echoes of turbines are replaced by the hush of wind, a reminder that the future, once so close, became history instead. Today, as France's TG5 lines age and global rail ambitions shift to Asia, the record of 574.8 kilometers per hour still stands, a monument to vanished confidence. The true cost of speed is not just technical, it is cultural. The future we build runs only as fast as we dare to imagine.